So our second speaker originally hails from Long Island, New York, and did his undergraduate studies in physics and astrophysics at Harvard. He is now, well actually, he just completed his PhD in physics at Caltech a month ago, so he's now a doctor. And he is here to talk about some of the research he did as part of his PhD dissertation about studying sounding rockets, sending them up above the atmosphere and taking deep images of the infrared cosmos. So please welcome Dr. Richard Fetter.
Thanks, Cameron. Super happy to be with you all today. I'm going to give a talk about what Cameron just said, sounding rockets with to do infrared astronomy, and well, I want to give you a flavor of the science that we do. I also wanted to take you through the life of working on a sounding rocket and sort of the process that I went through in 2021 with our flight integration campaign with CIBER. So, I guess to start, the question that I usually get when I start talking about these things is, why is it called a sounding rocket? This is a totally reasonable question, and it may not be for the reason that you think. So this actually goes back to a nautical term that was used many centuries ago, and this is a nautical term that is to sound as in to measure something. So if you can see on the right here, they have two men that are depth sounding. So this is where they're trying to measure the distance from the sea to the water floor. And in general, this is a word that is describing something that's probing something. It has other etymological roots in Romance languages for things like sonda, son, or sondear. And so a sounding rocket is just a rocket that is designed to measure something. There's been a long history, I guess, of rockets in general, but for sounding rockets, really it's been in the past century that there's been more development into them for scientific research. Many of these rockets were repurposed from the military, but some of these were designed in particular to do these sounding rocket measurements. And so in my research into sounding rockets, I learned that one of the first sounding rockets that was developed in the US, the WAC Corporal rocket, was developed right here in Pasadena at Gauset and JPL. And so this was used, and this was used for some time, and then a few years later, the US happened to be in control of a few V2 rockets, and these ended up driving the design of future rockets from there. And in the early phases, sounding rockets were used as a way to study the upper atmosphere, and also to study the spectrum of the sun. So, the general theme of these sounding rocket measurements is that you're trying to measure something that you just can't do from the ground, or it's really, really hard to do from the ground. And so, in the early days, these sounding rockets found a lot of success measuring the UV and the X-ray characteristics of the sun. They were also used for geophysics, and still are, to measure the aurora, things like this. I know they've also been used in times of solar eclipses, and they've also been used in microgravity research. I'll talk about their application in the near infrared, where we also need them. And so, just stepping back, why use a sounding rocket? There are a number of reasons. The first one, which I mentioned, is you want to bypass the atmosphere and maybe get to the upper atmosphere or get into what we call space. The second is that sounding rockets are relatively affordable to deploy, and so if you have an experiment, one route you could take is to fund a satellite class mission, but this is quite expensive. It turns out doing this with a sounding rocket can be much cheaper, in the range of $10,000 to $100,000 depending on how you count. I mean, the motors that we actually use are military surplus, and they're only like $3,000, but it's our finest equipment. So I guess along a similar line, these sounding rockets are really useful for demonstrating technology development. So if you want to deploy something on a satellite, but you want to demonstrate that it works in a space environment first, the sounding rocket platform is a really convenient way of doing so at a relatively cheap cost. Another reason that these are useful is for recoverability. So depending on the launch site that you go from, these rockets are actually recovered, and I'll talk about my experience at White Sands Missile Range where this was the case. But this can be really useful if you'd like to refurbish and maybe use the same telescope again, things like this. So I guess another thing to consider is geographic and timing flexibility. So here on the right I'm showing an image with a number of the sounding rocket sites that have been used or are currently used by NASA. And so I guess the two that I've worked at are Wallops Flight Facility in Virginia and then White Sands Missile Range in New Mexico. There's another in the US in Poker Flats, Alaska, and then there are a whole bunch of others that are distributed out here like this. So, depending on the type of science you're trying to do, certain sites might be better suited than others, and also certain times might be better suited than others. Like if you study the sun, and I'm by no means an expert on the sun, what I hear is that if you're trying to measure these solar flares, sometimes you're just waiting for the right moment when the solar flare is strongest. And so I remember working there that there had been some sounding rockets that were positioned and ready to go, but they were just waiting for maybe a week to get the go-ahead, and then they shoot up and they take their observations and they come back. For these reasons, sounding rockets are great, and I'd be remiss if I didn't mention another reason, because rockets. It's pretty fun to work on a rocket if you can. So the experiment that I worked on during my PhD is called the Cosmic Infrared Background Experiment, or CIBER for short. And so this was a sounding rocket payload that was designed to study something called the cosmic near-infrared background. It does so through a variety of ways. Just to give you a primer on what I mean by this near-infrared background, or people say this extragalactic background light, is basically a census on all of the light that's coming to us from outside of our Milky Way. And we just heard a great talk about JWST, where we're looking at these individual galaxies and we're peering really deep to measure these individual things. But studying the extragalactic background light requires more of a consensus view. Experiments like CIBER are well positioned to do this by trying to measure all of the incoming light over a relatively large field in order to make sure that our understanding of all of the astrophysical components that contribute to this light are accounted for. And this is a bit of a contentious field depending on who you ask, because some people make these measurements and they say, oh my god, we have way more light than we expected, what are we missing new physics? Other people do these measurements and they say everything is all right. The reality is that we need more information in order to probe this. And so CIBER is well positioned to do this as a small aperture telescope. So when you are launching on a sounding rocket, you need something that's going to fit on this rocket. And these rockets are not particularly large, I could basically hug them, and I wouldn't want to ride up. But the point is that you're limited by some of the mechanical and size constraints of the rocket in general. So on the right, I'm showing just a schematic of our layout. The actual experiment section on the rocket is fairly small. It's maybe 6 feet and maybe 1 foot diameter, maybe 1.5 foot. And so it's quite a mechanical challenge to design something that has your telescope, has all of your optics, all of your electronics and whatnot, and just fit inside this tiny thing. So CIBER 2, which I'm showing here, has something like 13 lenses packed in, which you can't see from this, but I think it's quite impressive that it does work. In the infrared, the reason that we want to do this on a sounding rocket is because like I said, these measurements are hard from the ground. And so if you're trying to do this measurement from the ground, you'd have to deal with the atmosphere. And at the wavelengths that we look at, the atmosphere is somewhere around 1,500 times brighter than the next brightest foreground, which is also a pain. So, getting into space is taking you a long way towards measuring the fainter diffuse light that's coming from outside of our galaxy. And so CIBER was developed at Caltech and JPL. So there were 2 generations of CIBER. So there's CIBER 1, which flew 4 times. CIBER 2, which I'll show some photos from now, flew three times on a Black Brand 9 rocket. And so these are actually Canadian rockets, but the US has been using them for some time, and they're driving the sounding rocket program currently. All right, so what are the other components that go into a sounding rocket? I showed you a schematic of the experiment section, but there are many other things that are needed to get these sounding rockets to work. So in no particular order, I'll describe these. All of these components are right in front of the experiment, but there's an attitude control system. So as the rocket is taking observations, and changing to different pointings on the sky. The attitude control system has gas thrusters, which are used to slightly adjust the position. On the way up, during the first few seconds, it turns out that navigating through the atmosphere can be quite hard, and so there's also a what's called an S19 boost guidance system, which is I guess this section here that has these fins. It may be hard to see. I took this photo from a poster in my room. It's my reference for these things. But this S19 system is used to navigate. There's also a telemetry system, which is to the right of the boost guidance system on this figure. And you might be able to see on these screens, there are 3 bands that are kind of copper colored. And so these are actually the antennas that are used to telemeter data down to a ground station. So for a lot of experiments, this is sufficient to send all of their data. For CIBER, we have these detectors that take quite a bit of data, and so we can send down a small fraction, but we really do need to recover the payload to extract the data in the end. Then a couple of other things. There's a side viewing star tracker. So this is looking to the kind of perpendicular to the axis that the rocket is moving. And so this is meant to, I guess, calibrate exactly where the telescope is pointing. We have a certain number of fields that we want to observe, and so this allows us to, take a look and see what are the stars that are visible with this star tracker, and do they conform with where we expect them to be. And so this is used to correct the pointing of the telescope once it's in space. And then there's a shutter door. So this is once we launch into space, this shutter door opens and we start taking observations. Once we're done, it closes and the experiment parachutes down. The last one I want to mention is the FTS, the Flight Termination System. This one is the one that scares all sounding rocket practitioners. So during the flight, in a separate room, maybe a mile away from where we are, somebody sits in a building with their finger on a button, and if anything goes wrong, if they see that the guidance is, if the rocket is going in the wrong direction, if it's heading towards Las Cruces, they take their finger off of the button, and that stunts the motors and basically ends the flight. I don't know if anybody wants to take a guess why they start with their finger on the button. Yeah, so I mean, it's much faster to react to take your finger off of a button than to press a button. And I guess it's a sort of dead man switch, but I don't want to think about that. So anyway, let's continue. Okay, so here now I'm going to show you the process of working on this sounding rocket and integrating with all of these components that I've mentioned, leading up to a flight. And so here on the right, I'm showing a photo from Wallop's flight facility. You can see all of the components of the rocket, aside from the motors, are assembled together. And the rocket is sitting on this vibration table. So vibration tests are one of a few tests that we do to make sure that our sounding rockets and our instruments are well prepared for the journey up into space. As you might imagine, these rockets go quite fast. I think with the Black brands, they hit Mach 2 in maybe 10 seconds. There's quite a bit of atmospheric disturbance and vibrations that come along with that. So these things need to be designed really well, and you really need to tighten every screw and make sure there isn't any screw loose. A single screw that's loose can totally bounce around and destroy your science. So we do a suite of vibration testing, these sign in random direction types of vibrations along each axis. And these are ramped up gradually up to something like 12 Gs RMS. And so this can mean that you can have 40 G kicks that are meant to capture if maybe the motor has some unexpected anomaly and has some sort of kickoff. I will say, sitting through this was probably the most stressful day of grad school for me. Sitting and watching them shape this experiment, that has several $100,000 of detectors and all these lenses, and we had kind of a losing streak passing these vibration tests leading up to this one in particular, but luckily we passed. And then there's a variety of other types of tests, like bend testing, where they move the rocket in lateral motion to check if there's any bend on the rocket. There's spin testing, because as the rocket goes up, it reaches something like 5 revolutions per second, and so you want to make sure that all of your electronics are functioning, in these types of situations. And then lastly, there's a balancing exercise that's done where where you basically want to make sure that the rocket is well balanced and it's not tilted to one side, and this is done to really like a thousandth of an inch accuracy. So they take this stuff quite seriously, and they have a really excellent crew of people at Walp's Flight Facility. All right, so once we passed our environmental tests, we were off to White Sands Missile Range to actually conduct our flight. So here I'm showing a map of White Sands Missile Range. North to south, it spans about 100 miles, and so because of this, it means that we can launch on the southern end of the range, and after the flight, it lands on the northern end, and that's where we can recover it. When I referred to non-recoverable before, just to clarify, this just means a flight that is maybe from close to the ocean that lands in the ocean, and there going in that you're not going to recover it. You hope in these cases that you recover it. So White Sands, if you haven't been, is a really beautiful place. It's known for White Sands National Park, which I'm showing on the left. These are some awesome photos from Grigory Heaton, who's also another CIBER member and was my roommate during this time. White Sands has been around for quite a while and has an interesting history. Among other things, it has a quite vibrant population of oryx. So these are originally from Africa, but they were some of them were moved to White Sands as a potential fertile environment for them. And I think they started out with something like 90, and currently there are like over like 1,000 that live there, and they just run around. You see them if you are driving, to work, or if you're going on the range. They're just all around, and really beautiful to look at. But with everything ready, this is we assembled the rocket. We put it on this Mario Kart type vehicle, and we slowly wheel it to the launching area. One of the last steps that we do before our actual flight is something called range horizontal / vertical. And so on the left here, I'm showing not a particularly special moment, but a view of what I call the blockhouse. So this is something like 200 meters from the launcher, and so this is where all the operations take place during the flight. And when you are here for these tests, they hand you basically a script that's several pages long with all of the commands and all of the checks that are done leading up to the actual flight. And the point of these exercises is to get the flow going for all of the checks that need to be done so that you can rehearse this. And so, when you're actually doing the hot count, you really want things to go smoothly. You don't want somebody to not be looking and realize that they have to say yes to something and then it slows down. And you want to make sure that everything is functioning well and that everybody is comfortable with what's going to happen. So the range horizontal vertical happens here, and afterwards we take a glory photo in front of the rocket. So hopefully you can see on the right, there's the rocket on the launcher, on the rail, with both of it's a two-stage motor that we used. So, and there we have some of the team that was part of the test. Okay, so once you've gotten to this, now we've gotten to the day of the launch. About 4.5 hours before T0, the hot count starts. And so once this starts, it's really game time. So at this point, the pyros have been installed. So I mentioned the flight termination system before. These are equipped right next to the motors to stunt if something happens. But everything is armed. The motors are ready to go. And here, I guess, I don't know if anybody can see, but there's some coils that you can see kind of wrapped around, these metal coils. During the flight, these are actually deployed, and these have weights that are used to de-spin the rocket. So I mentioned that the rocket is revolving at maybe 5 revolutions per second. But for an actual observation, you want to be static, and so these are meant to stabilize the rocket in flight. But this period is really hard to describe with words. How the suspense that is that you have going into this. You've worked on this experiment for maybe a year and a half more, and there's so much preparation that goes into characterizing the instrument, making sure that everything is functioning correctly, making sure that all the different components of the rocket are communicating with each other, and in these final moments, there's kind of a sense that you have to let go and just see what happens, which isn't the most satisfying, but it is exciting. Here's a photo of the rocket attached to the rail in this sort of shipping container. One of the cool things about this is that it's not that the rocket rolls out of the shipping container. It's that the shipping container rolls away from the rocket. And so, as you can imagine, you want a really solid base for the rocket launcher. Okay, so now I want to show you a quick video of our first flight. I know. Having a little challenge with this. They didn't teach me this in grad school.
It's not rocket science.
All right, settle down. All right. Don't mind these warnings. It's all right.
3, 2, 1, 0.
All right, so it really shoots up. The first 6 seconds, the first stage motor is going, and now you see that it's gone away. Thank you. In a few seconds, you'll see the second stage motor ignite, if you keep an eye out. Right there. All right, and so already by now it's going over Mach 2, and it speeds up to Mach 7 on its way up. So it reaches space in something like 1 minute. It's really crazy, but because it's a small rocket, you're able to get up relatively quickly. Let's see. I love looking at these videos because there are a million views of it, and they have them in slow-mo as well, from different viewpoints. This is really the big rocket go boom kind of experience. All right, that was All right, great. So we've launched the rocket. Hooray! And now, I just wanted to show you a few photos of the recovery. So luckily, this is not the experiment. This is the second stage motor that crashed into the ground and just totally incinerated the ground around it. But in the morning after our flight, there are 2 helicopters that are sent out. The first one is meant to go and locate this and the actual experiment payload. And the second one goes out and actually recovers the payload. So here are a couple of other images of the motor, not the experiment. And here's the actual experiment sitting in the beautiful New Mexico desert with the parachute unfurled like this. So we go in the early morning. If you're lucky and you're a future Astro on Tap speaker, you might get an opportunity to go on one of these helicopters. So yeah, I was lucky to take part in the experiment recovery for this. So we fly in on a Black Hawk helicopter. We make sure that everything is properly degassed. So there is sometimes a little bit extra gas left in the thrusters that you need to remove beforehand. And then, we carry this instrument payload, something like 600 pounds. So my back was hurting quite a bit afterwards. Here you can see a photo of the rocket door that I mentioned earlier, just totally incinerated. When we actually recovered some of the electronics, I had found that some of the wire solder had melted. So this isn't an easy journey for the telescope, but it ends up doing all right. And so lastly, we load it into the helicopter. We give a thumbs up and we bring it back. So great. Now I just wanted to highlight some of the science that we actually want to do with CIBER. So like I mentioned, CIBER was designed to characterize this near-infrared extragalactic background light. And so in this area, it's really still up to debate, how much light there actually is that is coming from outside of our galaxy in the near-infrared. Some studies have suggested that if you add up all the galaxies that we know about, this only makes up about half of the light that people measure. And so, there's a big question, is this actually real light, or is this some sort of foreground that we didn't account for before? Or is it an error in the analysis? Probably all three. But one of the ways that people have used this CIBER data, and in particular, I'm showing a figure from Yinting Cheng, who is somewhere here in the audience and has worked on CIBER. There she is. So I really like this photo because it kind of captures the essence of at least one of the ways we can look for this excess light. So what Yinting showed here is if I take these CIBER images and I stack my images on the positions where I know that there are stars, and then I stack these images on the positions where I know there are galaxies, we don't necessarily expect the same contribution. And this is because galaxies are quite messy. As galaxies evolve, they throw stars out into their into the outskirts of the galaxy. At more recent times, when galaxies are merging together, all these tidal forces can rip these stars away and distribute this light in a kind of diffuse manner that if you were just looking at the central core of the galaxy, you'd miss it. But using these CIBER data and using the stacking, you can see by eye that the galaxy stack just has more stuff in it, and this may be satellite galaxies that are orbiting the central, this could be truly diffuse light, but this is one way that we can quantify more concretely, and at least, add to our census, the different light that's, emitting in the near infrared. Another way that we can measure this light is taking a more global perspective. So rather than searching these individual sources, we can take our maps, we can mask out all of the bright things that we know about. So, we have a catalog from another telescope that tells us where all the bright stars and galaxies are. This figure is kind of highlighting, what's done here, where you mask them out, and then you use the statistical information in the remaining map to characterize any residual diffuse light in the maps. And so this is a method that's called intensity mapping. This is something that I worked on for the majority of my PhD thesis. And if you do the same with CIBER data, here I'm showing kind of a smoothed out version of this type of map. And so CIBER 1, this data that I'm using, has two broadband imagers at 1.1 and 1.8 micron. And the benefit of having these both of these bands is that we can look for light that's correlated across the bands, and we can also measure the color of this diffuse light. And so this has been a really exciting venture. By eye, you can play these games of comparing these two wavelengths and looking to see, like, are there correlated contributions from these? But we really need more studies and more characterizations in order to interpret exactly, if we find, some additional signal that we didn't expect before, where is it coming from? Is it coming from galaxies that we know about? Is it coming from our own solar system, from something that we didn't understand? Is it coming from something more exotic like dark matter? So I'm wrapping up this work, and if you check the archive, it should hopefully be up in a few months. But for now, I just wanted to thank you all for your attention, and I'm happy to take any questions. I'll start here. Okay.
So you're talking about light in a very general character. Yet, what is the actual spectrum that you're actually utilizing here? I saw 1 micrometer, so I assume, what is the spectrum that you're talking about as opposed to just visible?
Right. So I guess people in right. So the question was, I talked about light in a general sense, but what do I mean by spectrum? And I guess what are the ways that we use the spectra of the light? So there's kind of a dual use of the word spectrum in cosmology. There's the wavelength spectrum. So what is the color of the light? Kind of like what we heard in the last talk. And so there's also a second meaning, which refers to the spatial or the angular spectrum. So in this type of analysis that I was highlighting at the end, we calculate something called the power spectrum. And this is measuring the amplitude of the fluctuations in the light as a function of scale. So we can look and say, on small scales, how much fluctuations are there in the light? And then we can go to larger scales, going up to degree scales, and try and measure, what is the amplitude of the fluctuations in the light there. So like, in this case, I'm kind of highlighting the large angle fluctuations that you would measure in the power spectrum. But in reality, we use both the spatial spectrum and the frequency spectrum in order to interpret our results. So I saw a question here.
What is the duration of light? What altitude does it reach? Does it linger up there? Do it take weeks, later?
Right, great question. So the question was, how long does this each flight typically take? How high does it typically reach? And so typically this, if the rocket had launched at the beginning of my talk, it would have been done probably halfway through. It would have been back on the ground. So the total flight, it's maybe only about 15 minutes in total. And there's some stabilization that's done once it's in space. It takes about a minute to reach the altitude. So for a 2-stage rocket, you reach something like 300 kilometers as your apogee. For a 4-stage rocket, which we use sometimes, it can reach up to 600 kilometers, and I mean, the exact altitude depends on the mass of the payload that you're carrying. And once it's up there, you have these different components that are used to stabilize it. Serena? I hope you wouldn't ask this. So to answer your first question, so the first question was, has this been commercialized? So do you mean like, have sounding rockets been commercialized, or? To be honest, I'm not sure. I mean, these are mainly used for scientific purposes, and it's possible there are companies that do this, but to be honest, I'm not sure. The second question was, has anything gone wrong during using the flight termination system. And so CIBER 2 had 3 flights. The first one that I showed was a successful flight. The second one, about 30 seconds up, the Army received some sort of anomaly from its from a redundant radar that suggested it was going off course. And so for the 4th time in 20 years, they took their finger off of the button. Somebody buy me a beer. No. So this was quite unfortunate because everything else is on a timer. So when it thought it was in space, the rocket door opened, and so there's a huge cryogenic shock. It also didn't close on the way down, and so it landed with the door open, and so the door sheared off, and all these sticks and the rocks got inside. I didn't show those photos intentionally. By some miracle, the actual core components of the rocket were in okay shape, and actually, in about a year, the team refurbished it, and just this past May, I was there for a flight, for the 3rd flight, so yes. I saw in the back. Right. So the question was, what makes this science more amenable than doing this in space with a satellite or something like this? And so the answer is you can do this in space. And so CIBER ended up being a pathfinder for NASA's mid-X mission SphereX. Some of you may be familiar with this. I also go SphereX. I work on SphereX as well, and this is going to launch next year. The reason that it's great for a sounding rocket in particular is because you can do this at low cost, and for this type of intensity mapping science, you actually don't need a big mirror in order to do this. You can use these small aperture, small mirror telescopes that map a wide field, and so it's a complementary wavelength to JWST, but and so it's much shallower, but it covers a much larger region of the sky at any given point.
Let's thank our speaker, Richard Federer. Dr. Richard Federer.
Eight, 7, 6, 5, 4, 3, 2, 1, 0. Plus 1, 5. Plus 20. Plus 2, 5. Plus 30. Plus 35. Plus 40. 4, 3, 2, 1, 0.